All right, good morning. We are going to finish section 5.3, looking at zeros of polynomials, and I want to give a quick synthetic division review before we get into these techniques, because it's a good tool to have and something that we will make use of. All right, so again, what we're doing with synthetic division, and I have another lecture on this in more in-depth detail, but we're doing something like this. We're trying to divide a polynomial by, here, this only works for a first degree polynomial, so I will make a note of that here. So this has to be a first degree polynomial in order to do synthetic division. Otherwise, we have to use long division. Okay, and we're trying to divide negative 2x cubed plus 8x squared minus 9x plus 7 by the linear term x minus 2. Now, the way you do this in synthetic division is you write what we call our k value. Here, that'd be 2. And where do we get that? This is your k value. So here we're dividing by x minus k. All right, so k is 2. And then across the top, I list out my coefficients. So I have negative 2x cubed, 8x squared, minus 9x, plus 7, like that. Okay, now we have it set up. We're ready to do our synthetic division, and here's the process. You bring down your first term, and then you multiply. So here I'm going to multiply. So negative 2 times 2 is 4. And then here I'm going to add. All right, and that's not 4, it's a negative 4. So 8 plus a negative 4 gives me 4. And then once I do that, I just keep repeating the process. I say 4 times 2. 4 times 2 is 8. And then I add. Negative 9 plus 8 is 1. I hope this is making sense. Then I say again through the process, 1 times 2 is 2, 7 plus 2 is 9. And I've completed it. I've already done the division. All right, now, what are we looking at here? This right here is my remainder. And this right here are the coefficients for my quotient. So my quotient actually is, we'll call it q of x, is I started with degree 3, I drop the power by 1 for the quotient. I get negative 2x squared plus 4x plus 1. And again, the remainder here is 9. Okay, so that's the idea behind synthetic division. All right, and the thing about synthetic division is it's really fast. If I get a remainder of 0, that means then that I have actually found a 0 of the polynomial. For example, if I did this and the remainder had been 0, then I would have actually had x minus 2 is a factor of my polynomial. So if I find some of these, I can actually find the zeros of the polynomial. And that's what this section is about, is how do you find. So this could actually be called finding zeros of polynomials. That would probably be a better description of it. We're finding the polynomial zeros. All right, and there are several ways to do that. The first one is the rational root theorem, which I covered in the last lecture. We might have to reference that. If we do, I will make sure to use it. So the topic I want to look at now is called Descartes' Rule of Signs. And yes, that is René Descartes. Okay, so he wasn't just a philosopher, he was a mathematician as well, and a scientist. And we already have talked about the Cartesian plane named after him. And so this is Descartes' Rule of Signs. Now, this actually doesn't use synthetic division, but we'll use synthetic division later on. But here's what it helps me figure out. It helps me figure out if I have a polynomial, how many positive and negative roots does this polynomial have? Okay, and I think it's easiest to see with an example. And so this is about, we make use of counting changes in sign. Okay, so let me write that out. We're going to count the number of sign changes. What do I mean by that? Positive to negative, negative to positive. And we'll say f of x. And then f of negative x. Okay, we'll count the number of sign changes. We'll plug in x into f of x, count the number of sign changes. Then plug in negative x in f of x and count the number of sign changes. And the first one, f of x will tell me the number of positive roots. And I better put a star on that because it's not exactly the whole truth. I'll explain what I mean in a little bit. And then here in the negative, it's the number of negative roots. All right. So let me show you an example. I think this will make a lot more sense if I do an example as opposed to just writing out these long theorems, because I just don't know if that'd be a good use of our time when I can just quickly explain it. So example 2. This is example 2 from the text. Find the possible number of positive and negative roots. All right, and my polynomial here, the first one, we'll do a couple of them. The first one is f of x equals 2x cubed plus 3x squared minus 14x minus 21. All right, so we're going to do two things. First, we're going to plug in, or we're just going to look at the sign changes of f of x, okay? And so what I mean is, look, we go, if I'm just looking at the coefficients of my polynomial here, I start out positive, positive, negative, negative. How many times in this sequence did I change from either negative to positive or positive to negative? I only changed one time. There's only one sign change. Okay, this tells me then that I'm only going to have one positive root. All right, now let's look at, we'll write that up in a second. We'll summarize. Let's plug in negative x. Now, remember, if I square negative x times negative x is positive x. In fact, negative x for any even power is just going to be positive x. But for the odd powers, like x times negative x times negative x times negative x is negative x cubed. So if I plug in, here's what I'm trying to say. If I say 2 times negative x cubed plus 3 times negative x squared minus 14 times negative x minus 21, that simplifies like this. The odds now become negative 2x cubed. The evens, the sign stays the same. It's 3x squared. I get a plus 14x and then minus 21 like that. Now let's count the sign changes here. So let's see, we went from negative, positive, positive, negative. Oh, look, this time I have a sign change there and a sign change there. In my sequence, I went from negative to positive, and then later went from positive to negative. I have two sign changes. Okay, so then it says count the possible number of positive and negative roots. Okay, so for positive roots, let's say positive root numbers. Okay, so we're looking at the quantities. We only had one sign change in f of x, so we have one positive root. And I got that from here. We only had one sign change. Okay, for negative roots, how many sign changes did I have? I had two. So here's where we have to be careful, and this is why I put an asterisk here and here. We have two or 0 negative roots. What? Where did the 0 come from? So the way this works is, what's going on is if you have a complex number root, which we don't want to consider as positive or negative, okay? But if you have a complex number root, they're going to show up in pairs. So with these sign changes, we have to consider subtracting out multiples of 2. So what I'm saying here, let me write another example. Okay, so suppose we had 5 sign changes. When we did this, we had 5 sign changes in f of x. So here I'm just looking at the positive roots, then positive root numbers. It starts at 5, and then it goes down by 2s as much as I can. So 5, 3, 1. We're either going to have 5 positive roots, 3 positive roots, or 1 positive root, right? So that's why, hopefully that makes sense. We're just subtracting out 2 as much as we can. So that's why in this example here, for negative root numbers, I could either have 2 or subtract 2, 0. I either have 2 or 0 negative roots. For positive, I can only have 1 because you can't have, say, 1 minus 2 would be negative 1. You can't, that doesn't make sense. Okay, so this is a note here we have. Hopefully just kind of an explanation. Let's look at B part, and maybe this will make a little bit more sense. So this time we have g of x equals 3x cubed minus 10x squared. And then we have plus 51 fourths x minus 13 fourths. Okay. The fractions don't really matter, right? We're not actually factoring these things right now. We're just all we're doing is trying to figure out how many sign changes we have. Okay, so f of x, how many sign changes do I have? Let's see, we went from positive here, negative, there's one. Positive again, there's another one. Negative, there's another one. So actually here we went, there's a sign change, there's a sign change, there's another sign change, 3 sign changes. Right, and what I mean by that is if you're doing, think of them as a sequence, starting from highest going to lowest coefficients. I'm jumping from positive, negative, that's one. Negative, positive, that's a second. Positive, negative again, that's a third one. We have 3 sign changes. All right, now if I plug in, let's see, if I plug in negative x into this, so it's 3 negative x cubed minus 10 negative x squared, 51 fourths negative x minus 13 fourths. Let's see what happens. So simplifying this, I end up with negative 3x cubed. Remember, negative x squared is positive x, so I get negative 10x squared. And then I have negative 51 fourths x minus 13 fourths. Okay. Yeah. And so if I'm looking at my sign changes, let's see, I went negative, 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 negative. I actually have 0 sign changes here. So to summarize then, how many positive roots can I possibly have? So let's say number of positive roots. Well, I had 3 sign changes, right, in g of x. So that's either going to be 3 or 1, right? We have to subtract 2. We started at 3, subtract 2 as much as we can, 3 or 1. Number of negative roots. Number of negative roots, no sign changes. We have 0 possible negative roots. So if I'm trying to test numbers to plug in and see is this a 0, negative 1 is not a good idea because I already know I have no negative roots, right? So that's where Descartes' Rule of Signs can be helpful. And I hope that makes sense. Okay, now let's look at our next one. This one's called bounds on zeros. Okay, and let me get a number line here. I'm going to draw a number line. And I'm going to put up these 2 walls. And let's say all of our zeros are somewhere in this range. Okay, somewhere in between these pink 2 walls, okay? Then that means all of these numbers here are called upper bounds. Upper bounds on zeros. All right, so an upper bound means that if there's a 0 of this polynomial, it's going to be less than that upper bound. Okay, and you can have a bunch of them. Don't think it's just the wall. I mean, any of these count. Any of these satisfy that definition. A lower bound is just the opposite of that. So these are lower bounds of 0. So here, if I have a 0, if I know, for example, if I know -6 is a lower bound, then I know that that means all of the zeros of this polynomial have to be bigger than -6. Does it make sense? So let's say all zeros of a polynomial must be greater than the lower bounds and less than the upper bounds. Okay, so all the zeros are kind of trapped in between the upper and lower bounds. And the question is, can we figure out how to find upper and lower bounds? And the answer is yes. Okay, so here's the rule. And this is the kind of our theorem finding upper and lower bounds with these things. Okay, so let's pick a value k. So for synthetic division, right? So if in synthetic division, here x minus k dividing into p of x. All right. If the your last row, so the bottom row, if bottom row is all positive, k is sorry, an upper bound. All right, so if I do synthetic division and I get all positive, so if it's all positive, that means k is an upper bound. All right, now if the sequence is just constant change of signs, positive, negative, positive, negative, positive, negative, if the bottom row changes signs between any two terms, that doesn't really make it. Let's say if the bottom row, how about we say alternate signs? I think that makes sense. That means like this: positive, negative, so on. Then k is a lower bound. So the synthetic division, it helps us find our zeros, but not only that, if we happen to get something where it's all positive, that means we know that we don't have any zeros beyond higher than that one, that value. And likewise, if we get positive, negative, something like that, then we have found a lower bound. We know that all of our zeros are actually larger than that number. What if you get zeros in here? Okay, a zero can either be considered positive or negative and, when we're thinking along these terms. So the zero can actually satisfy either way. It's a wild card. All right, let me show you an example. Hopefully this makes sense with an example, okay? And if you have a question, of course, don't forget you can leave it in the comments. Example 3. All right, so here we're going to say, let's find, let's say find an upper and an lower, or a lower, right? Because there's a lot of them. There are a lot of upper and lower bounds of, here we have f of x equals 2x cubed plus 3x squared minus 14x minus 21. Okay. All right, so we're just going to do some synthetic division, and we can just kind of pick some numbers and just see what we get. Okay, so let's get something kind of close to 0 maybe, let's pick 2. I'm just going to pick 2. And we're doing synthetic division. So I have 2x cubed, 3x squared, minus 14x, minus 21. And remember, the way this works is you drop your first term, then you say 2 times 2. So you multiply here, which is 4, and then you add here. Okay, and we keep doing that. So 3 plus 4 is 7. 7 times 2 is 14. Add, you get 0. 0 times 2 is 2. Add, you get, what is that? Negative 19. Okay, now, did this satisfy either one of our two conditions? Did it remain all positive? No, it's not all positive. So it's not an upper bound. Okay, so not upper. I'll say upper B. Is it a lower B? Does it alternate positive, negative, positive, negative? No, it goes positive, 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 negative. It didn't jump back and forth, so that means it's not a lower bound either. So 2 is neither an upper bound nor lower bound, which means that there is a 0 higher than 2, and there's also a 0 less than 2. Okay, so let's try another value. Since we're at 2, let's try something close. Let's try 3. See what we get. Okay, so I'm going to run the same process. Bring down the 2. 2 times 3 is 6. Add. Right, we're adding here. 3 and 6 is 9. 9 times 3 is 27. Right? Negative 14 plus 27 is, let's be careful with arithmetic, is that 13. All right. 13 times 3 is, 39. And then 39 minus 21, be careful with arithmetic again. I believe you get 18. Okay, let's check our signs here. We went positive, 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 positive. We got all positives. That tells me then 3 is an upper bound. What does that, again, what does that mean? That means for all the zeros of this polynomial, they are all less than 3. And the funny thing is that they're not all less than 2, potentially. So there may be a 0 between 2 and 3. Okay? And what I should have said here on number 2 is it's not conclusive, right? It's not conclusive. And so we don't know, I misspoke here. We don't know necessarily if they're upper or lower bounds. It's just inconclusive. It could very well be, but it doesn't tell us. But for 3, for sure we know it's an upper bound. Okay? Sorry about that. Well, let's try another one. So I think if I did 0, that's not going to help. Let's try negative 3. All right, so we do 2, 3, negative 14, negative 21. We do our synthetic division and bring down 2. That's negative 6, right? 2 times negative 3 is negative 6. You add to get negative 3. You multiply to give me 9. So far, we're going plus negative. I get positive 9. Oh, that gives me a negative 5. I broke that. It's not a lower bound because I broke the pattern. But we can go ahead and finish just for practice. Negative 3 times negative 5 is 15. Add, we get negative 6 there. So look, we broke the pattern. We went positive, negative. That was good. Negative, negative, inconclusive. All right, so let's try another one. We'll just go down one more. 4. Okay, and we're just running this again. This is a really good practice for synthetic division. Bring down the 2. 2 times negative 4 is negative 8. Add to get negative 5. That's good so far. Negative 5 times negative 4 is 20. Negative 14 plus 20 is a positive 6. Hey, that's good so far as well. And then negative 6 times negative 4 is negative 24. A negative plus a negative is going to be negative. What is that? 45? Negative 45. I think this works. Look, we have positive, negative, positive, negative. Great. Negative 4 is a lower bound. So what this tells me, all right, now that we figured this out, what this tells me is here is, let me see. Here's negative 4. Here is, what was the other one? Positive 3. There are no zeros out here. There are no zeros. All the zeros, all the real zeros, are somewhere between negative 4 and 3. This is what we know. All real zeros are between negative 4 and 3. Now we said real zeros, right? Because if we're talking about complex numbers, the number line looks a lot different. It gets a little weird, but this we're only considering real zeros, and I hope that makes sense. That's a really cool thing. So now if we put together Descartes' Rule of Signs, which said what? Descartes' Rule of Signs told me the number of positive and negative roots possibly that I could possibly have, and now this bounds and zeros helps me limit the range and where they are. And if I pair this with what we call the rational root theorem, let's go ahead and do that. Let's go ahead and let's take this same polynomial. So this is example 4. It says use results. Let me see if I can spell results correctly. Results from example 3 and the rational root theorem to factor f of x, which equals, what's this polynomial again? 2x cubed plus 3x squared minus 14x minus 21. And please keep in mind that our previous techniques for factoring won't work on this polynomial, right? I mean, what would you try? That's a 2x cubed, sorry. What would you try? Factor by grouping? I don't think it's going to work. We don't really have a lot of techniques for this. Okay, so one, we already know. So we know from example 3 that all the zeros are between negative 4 and positive 3. Okay, we know that. So the only numbers we have to test are between negative 4 and positive 3. Now, what does the rational root theorem say? Okay, so let me go on for my lecture notes from the last lecture, and here's the rational root theorem, and let me explain what it says. Rational root theorem says, look, if you have a polynomial, this a sub n, x to the n, all we need is a leading coefficient, which is a sub n, plus blah, 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 we don't care, up to the constant, which is 0, a sub 0. All right, so all we're caring about at this moment is the leading coefficient and the constant term. All right, and if you have a rational root, which is a fraction, so this p over q, a fraction is a rational number. That's why we call it rational root theorem. If p over q is a root of this polynomial, then the numerator of my root divides the constant term, and the denominator divides the leading coefficient. Let me say that again. The numerator will divide the constant term, and the denominator will divide the leading coefficient. One more time, let me say it again so I remember. The numerator divides the constant term, the denominator divides the leading coefficient. Okay, so we're going back to our example. All right, so from the rational root theorem, we said that the numerator divides the constant term. So it's going to divide, well, let's figure out what is our constant term. So our constant term is negative 21, and our leading coefficient here is 2. So the numerator, we said, divides the constant term. So what could divide negative 21? 1, 3, 7, 21, right? And we're including plus or minus all of that. All right, so that's a short list now of what can be in the numerator. The denominator, we said, has to divide the leading coefficient. What can divide 2? We just get plus or minus 1, plus or minus 2. So possible roots. This is my possible rational roots, that is. Possible rational roots, P over Q, are all the combinations that we get from P and Q here. So that could be what? Plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 7 over 1, and 21 over 1. And then we do the same thing with 2. So 1 over 2, 3 over 2, 7 over 2, 21 over 2. And that now is a list of how many things? 1, 2, 3, 4, 5, 6, 7, 8, plus or minus 16 numbers. We get 16 numbers. Okay, so we went from an infinite number of numbers down to 16. And thanks to what we just learned with these bounds on zeros, remember, they all have to be between -4 and +3. I think we can eliminate some. So the actual list, so the shorter list, we can take out anything that's less than -4, anything greater than 3. Okay, so we get, let's see, we get plus or minus 1 still works, plus or minus 3 still works. This we can't use the 7s, right? The 7s are both too big or too little. Plus or minus 21, both are too big, too little. We can use the plus or minus 1 halves. 3 halves, remember, is 1 1/2, so we can use both of those potentially. 7 1/2 is what? That would be 3 1/2. So positive 7 halves doesn't work. We only get the negative 7 halves. And then 21 halves is what, about 10 1/2? So those get eliminated as well. Now we have gone from 16 numbers down to 1, 2, 3, 4, that's 8, 9. We went from 16 numbers, which is a huge jump from infinity, an infinite number of numbers, down to 16, and now we went from 16 down to 9. Okay, and how do we test if these work? Through synthetic division. So I'm going to cheat a little bit because I already know the answer. I'm going to pick one that doesn't work, and then we'll pick one that does work to show the difference. Okay, so let me think. Let's try 1. 1 does not work. Okay, I'm going to show you why it doesn't work. So again, we're dividing by 1, or we're dividing by x minus 1, and my polynomial again is 2x cubed, 3x squared, negative 14x, minus 21, and we are doing synthetic division. Right, so I'm going to bring down the 2. 2 times 1 is 2. We add, we get 5. 5 times 1 is 5. We add, we get negative 9. Negative 9 times 1, negative 9. We add, we get negative 30. And notice this is not 0. So 1 is not a factor. It's not a 0 of this polynomial. You only get a 0 if the remainder is 0. Okay, so we checked 1 off the list. Now we're down to 8 candidates, and we try again. All right, so let me think if I can think of a good candidate to try. I know. Let's try 3 halves. That seems reasonable. All right, so I'm kind of skipping ahead in the list. Actually, let's try negative 3 halves. I'm cheating a little bit. All right, so here we get 2, 3, negative 14, negative 21. And you know, in real life, you'd have to test these out. But I'm looking ahead just for the sake of time. But we could easily check 1, negative 1, etc. down the list until we get to negative 3 halves. And let's say we get 2. 2 times negative 3 halves. Well, the 2's cancel, we get negative 3. We add to get 0. 0 times negative 3 halves is 0. Add to get negative 14. Negative 14 times 3 halves is, well, let's see, it's going to be positive 14 halves times 3. 14 halves is what? 7. 7 times 3 is 21. Look at that. You add, we got 0. We did get a 0. So that means negative 3 halves is a 0. And it also means that my polynomial, f of x, it was called f of x, right? Yeah. F of x now is factored like this. X plus 3 halves. See, there's my 0. Negative 3 halves was a 0, right? So I get x plus 3 halves, and then here's my quotient. So that's going to be, I started at x cubed, I have to drop the power by 1, so I get 2x squared minus 14. And there it is. So can I find all my zeros? So find all zeros here. Well, yeah, it's factored. Remember, to factor it, to find your zeros, you take a factored polynomial and you set it equal to 0. So that tells me then that I could say that this, from here I get x equals negative 3 halves. And from this equation I have 2x squared minus 14 equals 0, which I could use quadratic formula on if I needed to, but I don't need to here. I get 2x squared equals 14, or x squared equals 7, dividing both sides by 2. So x equals plus or minus the square root of 7. X equals plus or minus the square root of 7. So there are my 3 zeros. Now, the square root of 7 is, well, let's think the square root of 4 is 2, square root of 9 is 3. So this is somewhere between 3 and 2, plus or negative, positive or negative. And does that satisfy our bounds? Yeah. We had to be smaller than 3, larger than negative 4. That works. And there are my zeros. So I used my combined information to figure this out. Okay, now let me quickly go over the Intermediate Value Theorem. And we won't spend a long time on it, but I'm going to just show you quickly. And if you're going to take a calculus class, we'll do a more advanced version of this in there. But here's the Intermediate Value Theorem. That we'll call this IVT. And here's what it says. If f of x is a polynomial, and f of a is negative, and f of b is positive, then there is another value we'll call c between, and here I should mention c is a real number, between a and b, such that f of c equals 0. What on earth are we saying here? Okay, if you have a polynomial, let me look at the graph will make complete sense, I think. So if I plug in a and I get a negative number, right, so here's a and I plugged in, I got a negative number. And when I plugged in b, I got a positive value. This polynomial, however this polynomial is designed, somewhere in between a and b has got to cross the x-axis. It has to, just by the way polynomials are. And so there's my value of c. And that's all we're saying. If you can plug in a value and get a negative, and plug in another value and get a positive, there's a 0 somewhere in between there. Or let me show you a quick example to explain this. So this is example 5. Show that f of x equals x cubed plus 3x minus 7 has a 0 between 1 and 2. Alright, so somewhere between 1 and 2. Alright, so all I'm going to do here is let's plug in f of 1 and see what we get. If I plug in f of 1, I get 1 cubed plus 3 times 1 minus 7. So that's 1 plus 3 is 4. 4 minus 7 is negative 3. Look at that. I get a negative value. If I plug in 2, I get 2 cubed plus 3 times 2 minus 7. That's going to be, if you have to think about it, that's 8 plus 6 minus 7. So that's going to be positive, right? 8 plus 6 is 14. That's 7. So that's positive. All right, so look, I plugged in 1, I was negative. Plugged in 2, I was positive. The graph looks something like this. Here at 1, I was at -3. At 2, I was up here at 7. This graph doesn't have any jumps in it, right? It's a polynomial. Somehow is going to cross the axis somewhere there, okay? So we're going to summarize our results like this. Since f of 1 is negative and f of 2 is positive, by the intermediate value theorem, there is a 0 between 1 and 2. Okay, now what do we know? I mean, what is that 0? Well, we don't know that. We just know it's between there. So sometimes finding it would be easy. If it's a rational root, we can use rational root theorem in synthetic division. If it's not rational, we're gonna have to start kind of guessing. So we plug in like 1.5, and so for example, the book actually does that real quick. If I plug in 1.5, I get the value, and you can do this in a calculator. You get 0.875, which is positive. So what does that tell me then? I play the same thing. I just know here's 1, here's 1.5. The root has to be somewhere between 1 and 1.5. I plug it in again. I plug in 1.4. I get a negative. F of 1.4 is now negative 0.056. So that tells me, see, I've narrowed it down. At 1.4 and 1.5, there is a 0 somewhere in between because I went from negative to positive from 1.4 to 1.5. So somewhere in here is a 0. Okay, and you just keep playing that game. You keep shrinking your window, and you can kind of somewhat pinpoint it to whatever degree of accuracy you need. Okay? Alright guys, we've looked at some advanced techniques here. Hopefully it makes sense. You'll probably have to go back and study them. That's fine. I encourage that. I encourage you to look at the last video about synthetic division and the rational root theorem in more detail. And I also encourage you to go back and look at polynomial long division because you're going to need to know all that stuff. If you have any questions, please let me know. I'll be glad to help you. I want you to understand. Hope you're staying safe. Thanks for watching, guys. We'll see you Wednesday. Take care.